manipulate them to find out what's going to hit the x-axis, the y-axis, where the vertex is going to be. And sure, we have done all of that, but there's one more way to be lazy when it comes to quadratics, and that's what we're going to do today. And what we're going to start with is the standard form of a quadratic equation. What we're going to do is essentially complete the square, but use the standard form instead. If you remember, the first step of completing the square was changing y into 0. But again, that's essentially saying where's it going to hit the x-axis, right? So if we can do that with the standard form, we should come up with a universal way to know where any quadratic is going to hit the x-axis. And that would be really nice, because I would rather have a formula than have to manipulate a quadratic into that intercept form, etc. So let's give this a shot. And we're going to complete the square using the standard form. So, as we said before, the first step is to change y to 0. I should also give a content warning that what we're going to do today may have given your parents and anyone else you know who've taken high school mathematics PTSD. But hopefully going about it this way will make it less traumatizing and at best maybe a little bit beautiful. It's not any more important than any other math formula that we've derived in mathematics, but it is a particularly clever one, and it's worth exploring. So the first step is to change y to 0. And the second step is to make sure that a is equal to 1. Now right now a is a, and I want to make sure that it's going to be 1. So I'm going to divide both sides by a. Now for the left-hand side, that means dividing every part by a. So a over a is just going to be 1. That's what we want. So we get x squared. And then b over a. And then c over a. And then 0 divided by a is still going to be 0. All right. Now the next step is to get rid of this c term. So I'm going to subtract c over a from both sides. Let's see what we get. I'm going to leave a vacancy. We end up with x squared plus b over a x. Oops. Let's not forget that in the previous step. Leave a space, negative c over a. All right. Now the next step is to force the left-hand side to look like a perfect square trinomial. So the way we do that is below, we're going to write our parentheses, quantity squared, and we want this essentially to be equivalent. We want to make this into a perfect square trinomial. The way we got this number is that we looked at whatever this number was, and we took half of it. All right, well, what is b over a divided by 2? Well, it's the same thing as times 1/2, so we just get b over 2a. All right, so I'm going to take half of b over a, and we end up with b over 2a. But I'm not done yet. I now need to square this and put it over here. We'll technically add it to both sides. So b over 2a, quantity squared. All right, well, b squared is just going to be b squared. 2 squared is just going to be 4, and then a squared is a squared. All right, so that's not so bad. Now, so I'm going to add b squared over 4a squared to both sides. All right. Okay, good. And all right, so we're good up there. Now, before I copy this down here, I'm going to want to combine those two fractions, but you'll notice that they don't have the same denominator. But they do both have a in the denominator. So basically, I just need to manipulate this first fraction so that it has a denominator of 4a squared. I can do that by multiplying it by 4a over 4a, right? Because 4a over 4a is just 1. I'm just multiplying this first fraction by 1. So we get c times 4a. That's going to give us I'm going to rewrite this elsewhere because it's getting a little bit crowded. All right. So we have x plus b over 2a, quantity squared, is equal to, right? So this is c times 4a. That's going to be negative 4ac all over 4a squared, right? 4a times a is going to be 4a squared, plus b squared over 4a squared. Now I can combine those two fractions, and I'm going to reverse their order because I like having addition first. So we end up with b squared minus 4ac all over 4a squared. Meanwhile, over here, we still have all of this garbage. Okay, so we should be good so far. But we have not yet gotten x all by itself. So at this point, since we have this perfect square trinomial over here, I'm going to square root both sides. Let's get a different color up here. All right. Now square rooting the left side, it's not too interesting. It's just going to be whatever is in the radical. So we end up with x plus b over 2a. And this is where it's going to get a little bit tricky. So that top part doesn't look like it's going to get any more simple. So I'm actually just going to separate it out, and I'm going to keep the top as it is. The square root of b squared minus 4ac. On the bottom, the square root of 4a squared, well, that's a perfect square. The square root of 4 is 2. And the square root of a squared is a. But remember, we superimpose this square root, so we have to remember to keep our plus and minus. All right, cool. We're almost there. X is still not by itself, so I'm going to subtract b over 2a from both sides. All right. And our grand finale is x equals. Now, these both have the same denominator, so I'm just going to give them all the same denominator of 2a. And so we're subtracting b, so it's going to be negative b plus or minus the square root of b squared minus 4ac. And la-ti-da, we have what is commonly called the quadratic formula. Now, typically, this is just something that one is meant to memorize. I know I had to do it, had no idea what it meant, didn't care what it meant, but hopefully this approach was a little bit better than what I had to experience. We didn't just memorize this out of the book. We just made this. We started out with the standard form, and using the method of completing the square, we got a universal formula that will always tell us where a quadratic is going to hit the x-axis. Well, that's kind of nice. No more manipulation, no more, fancy algebraic footwork, just this. I can take any quadratic, use this formula, and find out where it's going to hit the x-axis. That's kind of nice. let's give it a whirl. If we start off with, let's erase some of this garbage. We start off with a quadratic like this. Y equals 2x squared minus 8x plus 6. Now, I don't know, maybe you're a masochist. Maybe you want to do all of the heavy legwork. Maybe you want to make a t-chart and graph this little thing on a coordinate plane. Maybe you like hating yourself. But I don't. I'd rather not. I'd rather use this universal formula as a very convenient shortcut. So let's think about what this means. Remember for standard form, this is our A, negative 8 is our B, and 6 is going to be our C. So if I want to know where this quadratic is going to hit the x-axis, all I got to do is plug 2, negative 8, and 6 into this formula, albeit this ugly formula, and I'll get it. Let's give it a shot. So x is going to be equal to the opposite of b. So b is negative 8, so I'm going to take the opposite of negative 8, which is positive 8, plus or minus the square root of b squared, so negative 8 squared, that's going to be 64, minus 4 times a in this case is 2, c, in this case c is 6, all over 2a, in this case it's 2. Alright, now that looks like a lot of garbage, and it is, excuse me, but it sure beats the trial and error method of trying to factor all that stuff. And this might look scary, but it's just some very simple multiplication and subtraction and stuff. So let's just take this one piece at a time. I'm going to keep the 8 plus or minus the square root. All right, so 64 minus 4 times 2, that's going to be 8. 8 times 6, that's going to be 48. All over 2 times 2, which is 4. Now 64 minus 48, should have done this ahead of time to make sure I got my numbers. This is going to be 16, right? Plus or minus the square root of 16, and la-ti-da, that is a perfect square. So the square root of 16 is going to be 4, so we get 8 plus or minus 4 divided by 4. And we can see that that is going to give us two solutions. So if we take the plus first, these are the two solutions, 8 plus 4 divided by 4, and 8 minus 4 divided by 4. 8 plus 4 is going to get us 12. 12 divided by 4 is going to be 3. Then 8 minus 4 is 4. 4 divided by 4 is 1. And those are the two places it's going to hit the x-axis. Oh, that was way easier than what we were doing before. Now, you may look at that original one. Maybe you got really good at factoring, and maybe you could have made pretty quick work and found out that 3 and 1 are the x-intercepts. But what if we were to have a quadratic that hit the x-axis at an irrational number? What if our quadratic hit at pi? How are you going to factor a quadratic that has an irrational or transcendental even x-intercept? That's going to be a pain in the tuchus. So, don't bother. Forget factoring. We don't have to do it every single time. We now have a universal formula, the quadratic formula, whereby we can find where quadratic is going to hit the x-axis no matter what. Now remember there were some, so an example of this is if we had a quadratic that was not factorable. But then there were other kinds of quadratics that weren't just not factorable, they were weird in another way. So let's take one more example. And then we'll take a closer look at our formula. What if we had a quadratic that was y is equal to x squared minus 3x plus 4? All right. Now, you can probably learn see pretty quickly that I'm not going to be able to factor that into two binomials, so I'm going to have to try something different. For all I know, this is going to hit the x-axis at an irrational number. Who knows? But let's find out where it's going to hit the x-axis by using our universal formula. So again, our a in this case is 1, b is negative 3, and c is 4. So x is equal to the opposite of b, so it's going to be plus 3, plus or minus the square root. B squared, negative 3 squared is going to be 9, minus 4 times a, which is 1, times c, which is 4, all over 2a, and a is 1. All right. So let's just take this one piece at a time again. We're going to end up with 3 plus or minus the square root. All right, so 4 times 1 is 4, and then 4 times 4 is going to be 16. So we're going to have 9 minus 16. 2 times 1 is just going to be 2. All right, so 3 plus or minus the square root. 9 minus 16 is going to be negative 7. Oh, shoot. That's ugly. That's real ugly. But not something we can't do. Even though it's a negative 7, we can still make sense of this. 3 plus or minus I root 7 over 2. This quadratic has two imaginary roots, or rather, it's not going to hit the x-axis at all. If you were to graph this, it would look something like that. Actually, I think it's pretty close to the actual picture. It's not going to hit the x-axis at all. But that doesn't mean it doesn't have two x numbers that will bring the whole thing to 0. Because again, that's what we're working with, right? Where is this going to hit the x-axis? Where is y going to equal 0? This number, well, both of these numbers really, if inserted into the original quadratic, will reduce the entire thing to 0. Graphically, it doesn't make sense. There are no imaginary numbers on our normal coordinate plane. But I do love that even though it doesn't hit the x-axis, even though it doesn't make sense graphically, it still makes sense numerically. There's still a number, two numbers, that will reduce our original quadratic to 0. Y equals 0 when x equals either of these two numbers. It's kind of cool. Anyways, this should, well, hopefully, at least for me it does, opens up a lot of questions of what does it mean to insert an imaginary number into this kind of quadratic equation. Not sure, but maybe we can play with that. Anyways, I think that's sufficient for that. I do want to look at just one more piece.
I climbed to the top of a hill, but I had just missed the sign.
If we break it down into its two parts, two essential parts that is, so this is the way that we wrote it before, but if we were to break it up to make it the sum of these two fractions, one of these parts should look very familiar, this one in particular. We kind of already derived this kind of at the beginning of this whole unit. If you remember, this is what we discovered would give us the x-coordinate of our vertex, or in other words, the axis of symmetry. Right? So if we have our quadratic, that will give us this line. All right? And then that kind of makes sense why this has to be plus or minus if we're looking for where it's going to hit the x-axis. It's going to hit the x-axis here and here. We have the axis of symmetry, right? We know that. So all we need now is how far to the right and to the left is it going to hit the x-axis. And it's going to be the same on both sides because symmetry. Right? And that's what this whole thing is. This is our correction factor. This is going to say how far to the right and to the left of the axis of symmetry are these 2 points going to be. That's kind of lovely. It's built in right into it, into that plus or minus. Now, the top part of that fraction, namely the part under the radical, the square root of b squared minus 4ac, is often called the discriminant. And the discriminant can tell us a lot about our quadratic right
For the promise of
correction. If we're looking at the discriminant, and we look at particularly what's underneath the radical, that is b squared minus 4ac. I'm going to branch this off. If all of that is equal exactly to 0, in other words, if all of that kind of disappears, then that means we're going to have one x-intercept. Or in other words, the vertex of that quadratic is going to be on the x-axis. If everything in here kind of cancels out, we're going to have exactly one answer, right? Because if this is all 0, then the plus or minus goes away as well, and we end up with just that. So if everything underneath the radical goes to 0, we're going to have one x-intercept. If it goes to a number that is greater than or equal to 1, actually it need not be greater than or equal to 1. It just needs to be greater than 0, I should say. That's better. If everything under the radical is greater than 0, that is, it is a positive number, then that means we're going to end up with 2 x-intercepts, something like this. But if everything underneath the radical becomes less than 0, that is, it's a negative number, we're going to end up with 2 imaginary roots. All root means is, at least in this context, it just means where it's going to hit the x-axis. So to recap, if the discriminant, what's underneath the radical, is equal to 0, we're going to have one real number solution. If it's greater than 0, that is, it's a real number, or sorry, it's a positive number, then we're going to have 2 x-intercepts or 2 real roots. But if it becomes a negative number, we're going to have 2 imaginary roots. Okay, I think I've corrected all of the mistakes I've made. Now, let's